If we take our rules for conditional probability, the probability of A given B equals the probability of the intersection over the probability of the given. And we manipulate this formula to solve for A intersected with B. That boils down to taking the probability of B and multiplying it to the left-hand side of the equation. You'll arrive at this rule. The probability of A intersected with B equals the probability of A given B times the probability of B. For example, the saddle shop orders saddles in 3 different sizes. 10% are youth, 70% are average adult, and 20% are large adult. Now, knowing ahead of time we're going to be creating a tree diagram for this, I'm going to go ahead and get it going. We have 3 different sizes. We have youth, average adult, and large adult. 10% youth, 70% average, and 20% large. And if you add these numbers up, 0.1 plus 0.7 plus 0.2, you'll notice that they add to 1 or 100%. Some of the saddles that are ordered are English saddles. 15% of the youth, so we know ahead of time it's a youth saddle, and now 15% of them are going to be English saddles. Which means if you want to know, well, how many are not English saddles, that's 1 minus 0.15, that's 0.85. So each fork in the branch should add to 1 or 100%. 20% of the average adult saddles are English saddles. Which means if you want to know how many of the adults are not English saddles, that's 1 minus 0.2, 0.8. And 5% of the large adult saddles are English saddles. So if you want to know how many are not English, that's 1 minus 0.05, 0.95. This is our tree diagram to describe the situation. I went ahead and copied our Venn diagram to this page. In part A, we want to know the probability that a randomly selected saddle is an average adult English saddle. So we're looking for the probability of an average adult and at the exact same instant, English. And applying our previous formula, this is the probability of the saddle being English given that it's an adult saddle times the probability of an adult saddle. If you come into the diagram, the probability of an English saddle, if you come into the diagram looking at adult saddles and then looking at English saddles that are adult saddles, so the probability of an English saddle, given that it's an adult saddle, is 20%. So we have 0.2 in this position. Then the probability of even ordering an adult saddle is 70%. So we have a 0.7 in this position. And if we do 0.2 times 0.7, that will give back a probability of 0.14. In part B, we want to know what the probability is that a randomly selected saddle is an English saddle. To answer this question, let's go through and identify the positions of our English saddles. There's one right here, there's one right here, and one right here. So the English saddles fall into specific categories. This English falls into the category youth. So the probability that a saddle is English, well, it depends on what size it is. We have the youth in English saddle, then we have the adult in English saddle, and then we have the large adult in English saddle. Now we already found the probability of an adult and English saddle, and basically what we did was we took 0.2 times 0.7. You're multiplying the 2 branches. So we could use this same idea to get the values in the other 2 scenarios. If I want the probability of a youth saddle and English, I'm going to multiply the 0.15 times the 0.1. I'm finding this. And if I want the probability of a large adult in English, I'm finding the probability of an English saddle given it's for a large adult times the probability that it's an English saddle. I'm multiplying the 0.05 for the English saddle and the 0.2 for being a large adult. And again, we already have that answer from part A. This is 0.14. So I'm essentially adding up this plus this plus this. When you add these 3 boxes together, you're going to find that to have an English saddle, there's a 0.165 chance. Part C. A worker at the saddle shop discovers that an English saddle is missing from inventory. So ahead of time, we already know, we've been told the saddle is English. Now, what is the probability that this saddle is an average adult saddle? Well, to answer this, we need to know the probability of the intersection divided by the probability of the given. And that's what we found in parts A and B. We know that the intersection is 0.14, and we know that the given is 0.165. If you divide these numbers out, that means there's an 85% chance that this English saddle was for an average adult. Let's go back and review the rules for independent events. To be independent, the outcome of any one trial should not affect the outcome of other trials, meaning knowing information about one event should tell you nothing about the other. The information contained in B is irrelevant. The information contained in A is irrelevant to the information in B. So in other words, the probability of event A is the same whether or not B occurred. Go ahead and strike this out. I actually want it to read the probability of A given B, not B given A. So if we take this up here, the probability of A is the same whether or not B occurred. It means whether B happened or not. Knowing B happened gives you no additional information. The probability of A should be the same. So knowing B happened ahead of time didn't change anything. We still are just looking for the probability of event A. So if this happens, then you can say for a fact events A and B are independent events. Another way to determine if A and B are independent is to see if the intersection, probability of A intersected B, is the same as the multiplication, the probability of A times the probability of B. So for example, the contingency table below shows husband's height versus wife's height. And we want to know, are the events of a tall husband and a tall wife independent events or dependent events? To answer this, I'm going to use my rules for conditional probabilities. If they're independent, then the probability of having a tall wife, given that there's a tall husband, should be the same as the probability of just having a tall wife. Now this is one way. You also have to check it going the other way, which we'll do in a minute. So let's start with the given. We know ahead of time the husband's tall. That means this is all that exists for us. That's our sample space. Now out of these 60 tall husbands, how many of them also had tall wives? 18. Coming to the right-hand side of the equation, the probability of a tall wife, well, that's 50 wives that were tall out of 205 total. These two values will not come out to be the same number, so they're not independent events. Now, let's say for argument's sake that they had come back equal. Your next step would be to go in and check the other case. The probability of a tall husband given a tall wife. Is this the same as having the probability of a tall husband? If you get that it holds for both cases, then they're independent. If it comes back as false for one case, then they're not independent. If it comes back false for both cases, then they're not independent. A second way we could have checked whether or not these events are independent is to use the rule that the probability of a tall husband and a tall wife is the same as the probability of a tall husband times the probability of a tall wife. If this holds, then they're independent. So let's see, the probability of both, that's 18 out of 205. And we want to know, is this the same as the probability of a tall husband? So that's 60 husbands that are tall out of 205. And a tall wife. There's 50 tall wives out of 205. These fractions are not equal to each other, so it's not independent events. This is the works cited for this lecture.